During this lecture session on dynamic inventory problems under RISC, we will be referring to the two important issues. One is the probability distributions of demand and lead time. So you must have a good understanding of say the types of the distributions which say the demand probability distributions which are normally in use for modeling the problem or for formulating the problem. So this part we will discuss, and the second one is we will be referring to the problem formulation and the solution part, and particularly the cost based approaches will be discussing. Now, so let us first talk about the probability distributions for demand and lead time. So as we have observed that in any inventory control systems for modeling purpose, so you must have say thorough understanding of the types of demand. That means what are the characteristics of the demand and what are the characteristics of the lead time, and these the two factors essentially determine the values of the inventory control parameters. Now, as the problem is under RISC, that means in a given time period the exact the demand is not known, but what is known is the probability distribution. Similarly, in a given situation, so the exact value of the lead time is not known. What is known is the distribution of lead time. So as the problem under consideration is under RISC, we need to specify the probability distribution of demand as well as the lead time. A distribution may be expressed either in empirical form or in standard form. This point already we have highlighted. When you assume a distribution in standard form under a given level of significance, that is say alpha, say 0.05 or 0.01. So whenever you say that this is the distribution in standard form, like say exponential or normal or say uniform, and so obviously you refer to so what is the level of significance under so under this assumption, say alpha is 0.05. What is your confidence level? That means 95% of the time I conclude that the distribution is say the normal or the distribution is exponential. Okay. So whenever we conclude about the distribution in standard form, so the level of significance must be specified. We as a system analyst must be aware of the physical basis against this assumption. This is very, very important in fact, because any the distribution you assume, there must be a physical basis. That means first you observe the physical basis and then the physical systems related to a particular random variable, and then you can prove that this with all likelihood, say a particular so the random variable may be assumed to be normal or exponential. Is it okay? Or etc. There are many kinds of say the distributions you may be assumed. As per the standard distributions, as far as the standard distributions are concerned, the following distributions are used in the majority of the inventory items. So what are those? The first one, actually 3 or 4 types are commonly used. The first one is the uniform distribution. The distribution sometimes which is referred to as the distribution with the maximum ignorance. That means this distribution you may assume at the starting point. So the both discrete and continuous random variable, you may use the uniform distribution. So what we say that we use this distribution for modeling the system in the beginning. Past data are not made available, and each demand level or the lead time is equally likely to occur. Is it okay? So that is the basic assumptions we have, while we assume it to be uniformly distributed. The next important say the distributional assumption is Poisson, and Poisson distribution is used for discrete random variable. When probability of lower level of demand or lead time, relatively speaking, is assumed or found to be high. So this is the condition you must know. That means when you observe the system say the physically, so you must have these observations. That means the lower level of demand or the lead time is they are occurring say more frequently. So it is a good fit for small and infrequent demand where demand rate is fairly constant. For example, demand of a machinery spare part. So later on, when we'll take up say the numerical problems. So suppose you want to have an inventory policy for the machineries for a machinery spare, and so many a time we assume that that the demand for the machinery spare is Poisson. Is it okay? So there are many numerical problems, so we'll be referring to later on. The third important the distribution we assume in standard form, that is referred to as the exponential distribution for continuous random variable. When we consider the demand of an item at the retailer or the wholesaler stage in a supply chain, this distribution may be assumed. Okay, so there must be some the physical the basis for assuming for in this particular case that the distribution is exponential, distribution of demand for the items being used at the retailer stage or at the wholesaler stage. Then the fourth important say the distribution that we assume in many cases, that is the normal distribution for continuous random variable. Demand and lead time may be assumed to be normal when physically we prove that the level of demand or lead time is a function of several factors or the variables working at the upstream stages. Right. So this is the scenario. That means suppose y is a random variable assumed to be normal. It means that the value of y is dependent on the several factors, say n number of factors, x1, x2 up to xn. So and all these factors are occurring at the upstream stages, not at the downstream stages. That's why these are called the effective or affecting variables. Okay. So if you find such a situation physically, you can assume it to be that particular random variable to be normal. Before any standard distribution is used, it should be verified by a goodness of fit test. You may be aware of a number of goodness of fit tests like the chi-square test for the large sample and KS test, Kolmogorov-Smirnov test for the small sample, this etc., through the use of inferential statistics. So I presume that you are aware of this one or more of these goodness of the fit tests. If you are not aware of, so please go through these tests, particularly the chi-square test and the KS test, which you find in any textbooks on probability and statistics. You refer to the section on inferential statistics. While formulating a particular inventory control problem with an assumed distribution for demand and lead time, determination of relevant random variable needs to be known. For example, for AQ systems of inventory control, as the safety stock is to be determined during lead time. Okay, so safety stock is one of the parameters. Distribution of demand during lead time is to be known and specified correctly. That means for which time period the distribution of say the demand is to be known. So that the time period you must be able to specify, and this you can specify only when you come to know the working of an inventory control systems and under what condition during which time period there is a chance of say the overstock or understock situation, mainly the understock situation, and in order to avoid or to prevent the occurrence of the stock out situation, so you go for stocking some extra amount, which is referred to as the safety stock. Similarly, for the P systems, the distribution of demand during order period and lead time needs to be known and specified, because you need to determine the safety stock for the entire period that for the P systems, that is the order period and the lead time. Is it okay? So, because during this order period and the lead time there could be fluctuations of demand, and due to the fluctuations of demand there could demand and as well as the fluctuations of lead time itself, there could be there could be chance of the stock out. Now we'll be using these demand distributions while we model or while we formulate a problem. So we need to use the notations. So what are these notations? So let me explain. That means these following notations and expressions, certain expressions like say the mean or the standard deviations or the variance. Okay, so you will be using, and obviously you will be using their notations. So the following notations and expressions representing distributions, relevant variables and the parameters are used for purpose of problem formulation. Is it okay? So let us just discuss all these the notations and their the meanings in a systematic manner. Now capital M, this notation is used to represent lead time demand. That means the demand during lead time. Okay, so this is the demand in physical units, say 100 units or 1000 units. So when you refer to numerical problems, this point will be made very clear. So the lead M is the lead time demand, is considered a random variable, discrete or continuous. Okay, so this is all about capital M. What is FM? That means small fm, that is the probability density function for continuous random variable. Okay, what is PM? That means the probability mass function for discrete random variables. So this is the notations we used. That means the capital M, the small fm, and capital PM. Okay, so probability density function as well as the probability mass function. Now what is the mean demand during lead time? The notation is M bar. So this is 0 to infinity M Fm dm. That means this is the mean lead time demand for the continuous variable. For the discrete variable, what is the expression for M bar? That is sigma M equals to 0 to M max. That means the possible demand levels, M into PM. That means for each demand level, what is the corresponding the probability? So that is PM. What is the variance? Sigma square 0 to infinity M minus M bar square Fm dm. That means the variance of lead time demand when it is considered to be a continuous variable. When the lead time demand is considered to be a discrete variable, then the expression which the variance is sigma M equals to 0 to M max M minus M bar square PM corresponding probabilities, where M max is the maximum lead time demand. Is it okay? So this is the expression. So we have an expressions for M bar as well as the sigma square. That means this is the mean, this is the variance. For a Q systems of inventory control, the probability that there is a stock out situation during lead time. This is very important, because we must know the probability of stock out, and we keep extra stock or the safety stock or the buffer stock to prevent the occurrence of the stock out. So the probability of stock out, that means M is greater than equals to B. What is capital B? Capital B is the reorder point. That means when during lead time the demand is greater than the reorder point, obviously there will be a stock out situation. So this is integration capital B to infinity Fm dm. So it is a continuous variable, and if it is a discrete variable, then obviously this is sigma M equals to B plus 1 to M max PM, and the expected stock out quantity is given by, this is the notations we have used. That means expected stock out quantity, what is the condition? That means M is greater than B. So that is B to infinity M minus B Fm dm, that is for the continuous variable, and for the discrete variable this is sigma M equals to B plus 1 to M max M minus B PM. Now let us now talk about with this the basic understanding of the distributions and their parameters with the notations the known. Now let us talk about the problem formulation and the solution. So that is the most important aspect, and first we will discuss the cost based approach. The problem under consideration is to determine the parameters order quantity and reorder point for Q system, and order interval and maximum inventory for the P system. When the stock out costs are known, demand is constant or variable, and the lead time is constant or variable. The stock out cost can be estimated and valid in one of the four ways in a given situation, like the stock out, how it is responded to. That means there could be back ordering case, so corresponding back ordering cost per unit that may be relevant, or the back ordering cost may be assumed to be fixed one irrespective of the amount of shortage, and so this is referred to as the back ordering cost per outage. Now the stock out may be responded by, say, the lost sales. So the corresponding lost sales cost may be estimated per unit basis, or in certain cases the lost sales cost can be estimated per outage basis. Now hence when we apply the cost based approach, the problems can be classified under the following four categories. So what are those? First one is the constant demand and constant lead time. Now this particular problem already we have discussed. That means when you refer to, say, the static inventory problem or dynamic inventory problem under certainty. So essentially we refer to this kind of problem, constant demand and constant lead time. The second one we need to discuss, that is the variable demand but constant lead time. The third alternative is constant demand and variable lead time, and the fourth alternative is variable demand and variable lead time. So obviously the number one type we have already discussed. The other three we will be discussing during this week. Out of these four categories, the problem under category 1 has already been discussed under dynamic inventory problem under certainty. So the other three categories are relevant to be discussed in the given context. So let us talk about say the category 1 problem, that means variable demand and constant lead time. Okay, so and what we assume that the demand and lead time are independent with each other. That means the approximate method we will be using initially, and later on definitely the exact method also we will discuss. So, the inventory profile of this problem, that means category 1 problem, is like this one. That means here the Q is the order quantity, S is the safety stock, B is the reorder point, and L is the constant, say the lead time is constant, this is L. B minus S is the expected lead time demand, that means this is the S, that means expected lead time demand is this one, expected lead time demand is this one. B minus J is the minimum lead time, B minus J is the minimum lead time demand, and B plus W is the maximum lead time demand. That means W is negative, that means this is the back ordering. You are unable to fulfill this amount, that is W, but the customers are waiting. That means in the next cycle definitely you try to fulfill his or her demand, and that demand is back ordered, and that amount is W. So, B plus W is the maximum lead time demand, and probability that M greater than B, it means the stock out probability. Is it okay? So, this is the stock out probability. So, when back ordering cost per unit is considered valid. Now, so that is the first case. So, what is the safety stock? So, safety stock is expressed as S. S is the notation we use, 0 to infinity B minus M FMDM. So, after the simplification we have this expression B minus M bar. So, what is B? B is the reorder level, and M bar is the average demand during lead time. So, expected annual safety stock cost. So, that you first have say the expression for the expected annual safety stock cost, and you try to minimize this cost. So, it consists of two parts, annual holding cost plus annual say the stock out cost. So, this notation TCS equals to S into H, capital H is the holding cost per unit per year, A is the safety say the stock out cost, say the per unit, and R is the yearly demand, and Q is the order quantity, which already you have determined, and this is the expected number of units short. Is it okay? So, A is basically the stock out cost per unit short. So, this is the expected number of units short, and you please go through these expressions, and so we have the expression for TCS. So, H is the holding cost per unit per year, A is the back ordering cost per unit, R is the average annual demand in units, already I have mentioned. So, taking the first derivative of TCS with respect to B. So, the B is basically your decision variable, and setting it equals to 0 for minimization of expected annual safety stock cost, we get the following expression, that means the optimal probability of stock out for determination of the safety stock and reorder point. So, ultimately we get this expression, that means probability that M is greater than B, that means the probability of stock out is equals to HQ by AR. The expression is valid for both discrete and continuous probability distribution of lead time demand M. So, here is one numerical example. So, what is the optimal reorder point for the inventory problem specified below and in the given table? So, these are the values: R 1800, C is 30, F is 15%, that means at a holding cost fraction, P is 2, and capital A is just rupee 1 per unit back ordered. So, what we have, that means first we determine the order quantity, that is one of the parameters. We use the basic the classical EOQ formula, and we get a value of 600 units. So, all the data are known, and you determine Q star, that means optimal say order quantity for the given item, and the probability of the stock out, the notation is that probability that M is greater than B, that is HQ by OR. Already we have derived this expression. So, this value is 0.10. By considering the last column in table, so we will show you the table for probability M greater than B probability stock out, that means this is the condition to be specified, and under these conditions what is actually what will be your say the reorder point. So the computed value is between 0.05 and 0.11. Selecting the smaller value 0.05, the reorder point is 56 units. The fixed order size system should function with Q equal to 600 units. That means is the Q systems of inventory control for the given item, and B is 56. So this is the table we have. That means the lead time demand M. So these are the possible lead time demands we have. Corresponding probabilities are given. So when you add all these probabilities, this is 1. You add one more column, that is the probability of stock out, probability that M is greater than B. So these are the values. So if it is against 48, that means what is the probability of stock out, that is 0.98. If suppose your the reorder point is 49, then what is the probability of going stock or going stock out, that is 0.95. 1 minus 0.02 minus 0.03, 0.95. So this way you calculate, and ultimately you will find that against 0.05 probability of stock out, the corresponding value of M is 56, and against 0.11 probability of stock out, the corresponding value is 0.55. Now our the benchmark value is 0.10. So that's why our you say that against 0.05 probability of stock out, you have the corresponding demand during lead time, that is 56, and that's why the reorder point is 56. So similarly, when back ordering cost per outage is considered, that means in the next case we assume that the stock out cost remains the constant, and the back ordering, it is a back ordering situation, remains constant irrespective of the amount shortages. Okay. So if this is the assumption, then the expected annual safety stock cost TCS is given by SH plus GR by Q. Now what is the G here? Capital G is nothing but the back ordering cost per outage per unit, and this is basically the probability of going out of stock. Is it okay? So that means integration B to infinity Fm dm. So this is the the simplified expressions, and then when you take the first derivative of TCS with respect to the reorder point B and setting it to 0, the following relationship is obtained. So what is that relationship? Relationship is FB is equals to HQ by GR. Is it okay? So here is another numerical example. So the weekly demand is normally distributed with a mean of 20 units and the standard deviation of 4. So what is the optimum reorder point if holding costs are ₹5 per unit per year? That means the value of H is given. The back ordering cost is also is ₹10 per outage. The order quantity is 26 units. That means you don't need to calculate separately. The order quantity is already given, and the lead time is 1 week. So here your main purpose is how to get the value of the reorder point. So you have these expressions, that means it is normally distributed. So what you try to do, you have the expression for FB. Now this is to be expressed in standard deviation units as far as the normal distribution is concerned. So this is FZ. So we get the FZ value. So FB value is HQ by GR. So when say the sigma is known, already the value of sigma is specified. So FZ value is 0.05. You refer to the standard normal distribution, and this is the ordinate. That means an ordinate of 0.05, the small FZ, that gives a value of capital Z 20.03. So hence the safety stock is Z into sigma, and this value is 8 units we have computed, and the reorder point B is M bar plus S. So M bar is 20 and S is 8. So the reorder point is 28 units. Is it okay? So this is the solution, and we have just introduced the concept of the cost based approach, and under the cost based approach we have considered the two types of cost. One is the back ordering cost, the per unit, and the second one is the back ordering cost, the per outage, or we have assumed that there is the fixed out of stock cost or the back ordering cost. So, the other types of costs we'll definitely consider in the lecture sessions. Thank you.